Okay, so if you haven't printed out the notes that I'm using for this video, pause this video, come back to it, and print out the notes on Blackboard for this video so that you can copy as we are going through them. So we learned how to do Taylor polynomials already. A Taylor series is just a Taylor polynomial that goes to infinity. And don't forget, a Maclaurin series is just a Taylor series centered at 0. Alright, so example 1, we'll just go through a couple examples. Find a Taylor series for e to the 5x centered at c equals 2. Give the first 4 non-zero terms and the general term, which would mean that we would have to find f of x, f prime, f double prime, the third derivative, and plug in 2. So let's go ahead and do that. So f of x is e to the 5x, f prime of x is 5e to the 5x, f double prime of x is 25e to the 5x, f triple prime 125e to the 5x, and that's all we need. Plugging in 2, we would have e to the 10th, f prime of x of 2 is 5e to the 10th, f double prime 25e to the 10th, f triple prime 125e to the 10th. Okay, and then we make our Taylor polynomial. We start with e to the 10th, and then we add 5e to the 10th times x minus 2 plus 25e to the 10th times x minus 2 squared plus 125e to the 10th times x minus 2 cubed plus ... And then don't forget to divide by factorials. So we have 2 factorial, we have 3 factorial, and 5n e to the 10th over n factorial, x minus 2 to the nth. Sum from our summation notation would be n equals 0 to infinity of 5n e to the 10th over n factorial times x minus 2 to the nth. Okay, so there are 3 special Maclaurin series you must know. These are the series for e to the x, sine x, and cosine x. So take a minute and do e to the x, cosine x, and sine x. Pause this video and then try them on your own, and then check your work with the answers that I have posted in a second. Alright, so if you look at e to the x should be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial. So the sum of the series would be x to the n over n factorial from negative infinity to infinity. To derive a series for sine x, you would have 1x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. So it's alternating, which is why you would need the negative 1 to the nth. And then each exponent is odd and each factorial is odd, so it's x to the 2n plus 1 over 2n plus 1 factorial. That also converges on negative infinity to infinity. Cosine x is similar, only it has even exponents and even factorials, still alternating, so it's negative 1 to the nth, x to the 2n over 2n factorial from negative infinity to infinity. Make sure you memorize these 3 special series, because if you do, it makes doing multiple choice and some free responses a lot easier on the AP exam, and it takes a lot less time. So if you memorize them, then it'll be a lot easier for you. There are 3 special things that you can do, or 5 special things that you can do to series like these. You can substitute into the series, you can multiply or divide the series by a constant and or variable, you can add or subtract 2 series, you can differentiate or integrate a series, and you can recognize it as the sum of a geometric power series. So we'll do all those in the following examples. So given f of x equals sine x squared, let's say that we want to find the first four non-zero terms and the general term. Well, all you have to do is sub in x squared for x in the original sine x series formula. So since sine x was 1x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus negative 1 to the n over x to the 2n plus 1 over 2n plus 1 factorial, all you have to do is plug in x squared in for everywhere you see an x, and you have your series, Taylor series for sine x squared. So here I am plugging in x squared everywhere I see an x, and then you can just rewrite the general term at the very end, and you have your series for sine x squared instead of having to do all of those derivatives over and over and over again and coming up with a new rule. So similar to substituting in, you can multiply the series by a variable. So if you have x cosine x, find the first non-zero terms and the general term. Let's start with cosine x, which is 1 minus x squared over 2 plus x squared, x to the 4th over 4, all even numbers, plus negative 1 to the n, x to the 2n over 2n factorial. And if I want that multiplied by x, all we have to do is multiply everything by x and distribute the x into each term. X minus x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial plus negative 1 x to the 2n plus 1. So notice how the exponents are odd now, so I did x to the 2n plus 1 over 2n factorial. Okay, find a Maclaurin series for h of x equals e to the x plus e to the negative x over 2. Well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial. And e to the negative x, all we have to do is plug in a negative x everywhere we see an x. And then I'm going to add them. I end up with 2. The second term cancels out. Then I have 2x squared over 2 factorial plus 2x to the 4th over 4th factorial. So I'm going to end up with 2x to the 2n over 2n factorial. And then if I take both of those and I divide it by 2, my terms are going to be this. Alright. Now, the hardest part of these Taylor and Power series is what we're doing next when we're going to differentiate and integrate them. So, if you look at this series right here, it kind of looks like 1 plus 3 over 1 factorial plus 3 squared over 2 factorial plus 3 cubed over 3 factorial plus 3 to the n over n factorial. Well, if you recall that e to the x is 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the n over n factorial, then the series above is probably the same thing as e to the x, only with 3 plugged in. So you can assume that the sum of the series above is e cubed. For the next one, it kind of looks like sine x, because each of the factorials at the bottom are alternating odd numbers, and the exponents are odd numbers. So it kind of looks like the sine function with 2 plugged in. So that series above is just equivalent to sine of 2. And for the last one, you should notice that that's a geometric series with the first term being 1 r being negative 2/3, so it's 1 over 1 minus negative 2/3, and you should get 3/5. Okay, at the bottom, you can differentiate and integrate each sequence or series, and that is totally fine. The radius of convergence is going to be the same as the original power series, but the interval of convergence may differ as a result of the behavior at the endpoint. So make sure that every time you take the derivative or integrate it, you have to reevaluate the endpoints as you're going along. I'll show you an example next. Okay, if you recall, this function looks like a geometric sum, with a1 being 1 and r being x. So we can write f of x as the geometric sum of, starting at 1 to infinity, of 1x to the n minus 1. This is going to converge when the radius is less than 1, so it converges from -1 to 1. Part B says, use your answer to A to find the Maclaurin series for f prime of x. Give the first 4 non-zero terms in the general term. For what values of x does the series converge? Well, this is the original function. So the derivative will be nx to the n minus 1. This might be a little bit confusing because in the original series I used n starting at 1, and in part B I used n starting at 0. You could have started at 1, that's totally fine, but for me it was just easier to start at 0 for f of x because the derivative just looks a little bit nicer than it would if I started at 1. But either answer would have been completely accurate. It just depends on your personal preference. So f prime of x is 1 plus 2x plus 3x squared plus nx to the n minus 1. This is going to converge when absolute value of r is less than 1, so in between 1 and -1. But remember what I said, that you still have to test endpoints just to make sure that the interval did not change. So testing -1, this diverges by the nth term test. Testing 1, this also diverges by the nth term test. So the interval of convergence has no change. It's kind of hard to see on my paper, so that's why I asked you to print out your own copy, but it says use your answer to B to find the sum of the infinite series. Well, our answer to B was 1 plus 2x plus 3x squared plus 4x cubed plus nx to the n minus 1. If you notice the series above, it looks just like f prime of x, only with 1/3 plugged in for x. So the power series above represents f prime of 1/3. Well, how do you estimate the exact value of f prime of 1/3? We already know that f of x is 1 over 1 minus x from the original problem. So if we take f of x and take the derivative of it, I should get -1 times 1 minus x to the -2 times -1 chain rule, and then plug in 1/3 for f prime. I should be able to get a value of 9/4 and say that the sum of that series above is equivalent to 9/4. It's kind of hard to see, but that's how the connection is made between the series and the actual original function. So the series is just a different way of writing the function. In the same respect, you can also integrate power series. So let's do the next part, part D. Use your answer to A to find the Maclaurin series for the integral from 0 to x of f of t dt. Okay, so our original f of x was 1 plus x squared plus x cubed plus x to the nth. So our integral from 0 to x of f of t dt will be x plus x squared over 2 plus x cubed over 3 plus ... x to the nth over n. This is also going to converge on the interval -1 to 1, we need to test the endpoints. At x equals -1, notice that this series is alternating, decreasing in magnitude, and also the limit equals 0, so this part is going to converge. At 1, though, it's going to diverge. It says nth term test, but it's not nth term test. Cross that out and write harmonic series. Anyways, so when you go back up to the top, you would write an equal sign on the interval of convergence for -1, but not an equal sign at 1. Okay, so now use your answer to D to find the sum of the infinite series 1/3 plus 1 over 3 squared times 2 plus 1 over 3 cubed times 3. Well, recall that from part D, our integral is equivalent to x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4. So the top part should be equal to the integral from 0 to 1/3 of f of t dt. So integrating 1 over 1 minus x, we get negative ln absolute value 1 minus x evaluated from 0 to 1/3. Plugging in, and we get negative ln of 2/3. And so that is what that series is equal to. Alright, for homework, do the worksheet 2 posted on Blackboard under this section, and be prepared to give me questions if you need it. Alright, see you later. Bye.